So let's talk about our second potential energy that we'll deal with in this class, and that's elastic potential energy. So if you have a mass attached to the end of the spring, and you exert some external force that pulls that mass away from equilibrium, you know that there's going to be a spring force that points back towards equilibrium. If you compress it in the other direction, so here we've stretched the spring out by pulling the mass one way. If you compress the spring by pushing the mass in the other direction, again, there's going to be a spring force that opposes the way that you're pushing, and so again is going to try and push the mass back towards equilibrium. So what does an elastic force want the mass to do? Well, it wants to pull the mass back to equilibrium. So you increase the elastic potential energy, which we're going to designate as U sub S, the S for spring, of course. So you increase the elastic potential energy by moving the mass away from equilibrium. The elastic potential energy decreases when the mass moves back towards equilibrium. So basically, so again, this is when the mass moves in the direction the spring force wants it to go, and the spring force always wants to push it back towards equilibrium, then the spring force will do positive work, which means that the potential energy will decrease. Again, the calculation on this one is basically exactly the same calculation we did for calculating the work done by a spring. We've just got this minus sign out in front. So we know the change in the elastic potential energy is going to be negative, the work done by the spring. The work done by the spring actually had a minus sign sitting out in front, so this is just going to cancel that. And so we're left with the change in the elastic potential energy is equal to 1/2 K, K again is our spring constant here, times the final displacement from equilibrium squared minus the initial displacement from equilibrium squared. So again, these X's are defined to be displacements from equilibrium. How far away have you stretched or compressed the spring? So we said that the elastic potential energy increases when you move the mass away from equilibrium. Well, all that means is that the final displacement value is larger than the initial displacement value. So you're taking something bigger and squaring it, subtracting something smaller and squaring it. Sure enough, that means this term inside the parentheses is going to be positive. K is always positive, so that would mean that the change in the elastic potential energy would be positive. You increase by moving away from equilibrium. So that checks out. We said you decrease by moving towards equilibrium. And in moving towards equilibrium, all that means is that your final displacement is less than your initial displacement. So again, when you take the final displacement squared minus the initial displacement squared, you're going to have a smaller number minus a bigger number. That's going to be negative, which means that I will decrease the elastic potential energy by moving back towards equilibrium. So again, that checks out. And just like with gravitational potential energy, if you want to talk about the elastic potential energy, what you really mean is the elastic potential energy relative to the point where it equals 0. Now with our gravitational potential energy, we had a choice about where we were going to put the 0 point. With elastic potential energy, we're always going to pick the 0 point to be at equilibrium. So here's sort of, basically we're going to say that we don't have a choice, we're always going to put it at the equilibrium point. And then we can calculate the elastic potential energy as just 1/2 kx squared, where again x is basically defined to be the distance that you're either stretching or compressing the spring. So one of the interesting things to note about this equation is the elastic potential energy can never be negative. It can be 0 because you're at equilibrium, and so x is 0. Or it will be positive regardless of whether you're moving to the right or to the left. So it doesn't matter whether you're moving in what would be considered a positive or negative direction, because you're just squaring that distance anyway. So the elastic potential energy is never negative. Now the change in the potential energy, again, can be. The change in the elastic potential energy will be negative when you move back towards equilibrium. But the value at any point relative to the 0 point will never be negative. It will always be either positive or zero.